Hi, my name is Tommaso, and this talk is going to be about robust recovery for stochastic block models. This is joint work with Jingqiu, Rajai, Nasser, and David Steurer. Okay, so let me start by introducing the community detection problem. We are given a graph as the one that you see on the left, and this graph has no apparent community structure. But then it turns out that if we partition the vertices carefully, as you see on the right, then there's indeed some community structure. So the goal, given the graph on the left, is to find the communities on the right. Now, the stochastic block model is one model to generate these kind of graphs. And for people familiar with it, here we're going to discuss only the symmetric two communities case. So this is a joint distribution over a vector X, which we call the community vector, and a graph G. So X is a vector with the entries that are either -1 or +1, and which corresponds to the label of the vertices. And then an edge is in the graph with some probability that depends on whether the two vertices are in the same community or not. So for example, here we have two communities, the red community and the blue community. And now red or blue edges appear with probability 1 plus epsilon times d over n. On the other hand, the green edges, which go across community, appear with probability 1 minus epsilon times d over n. Now, I want you to think of epsilon as some small constant and d as some constant. So d is the expected average degree of the graph. So we'll mostly talk about sparse graphs. But of course, many of the things that we say carried over for denser graphs. Okay, the idea of recovering the communities can be formalized as the weak recovery problem. So here we're given G, sample from the SBM, and we wish to design an algorithm that outputs a vector which in expectation has constant correlation with the community vector. So this is what the expectation in this slide is saying. And it turns out that there is an amazing result about weak recovery, which essentially states that there is a sharp threshold called the Schatten threshold, below which it's impossible to perform weak recovery. But as soon as we are above this threshold, then efficient weak recovery is possible. The threshold is d times epsilon squared larger than 1. This result is amazing, and also it makes the stochastic block model a very useful model to study for average case complexity. So this short phase transition was first conjectured roughly a decade ago and proved a few years later. And then algorithms have also been developed for a more general SBM model, but we're not going to discuss that. So what we are interested here in here is a slightly more general adversarial model. So we sample a graph from the stochastic block model, and now an adversary looks at the graph and arbitrarily changes a constant fraction of the edges. So remember, the graph is sparse, so the number of edges is linear in n. And so the adversary is allowed to change rho times n edges. So you should think of rho as some constant. And then we're given this perturbed graph G prime. So what we want to understand is whether weak recover is still possible at the Schatten threshold, whether the threshold changes, whether the threshold changes only for efficient algorithms, and want to answer this kind of questions. So if we look at algorithms that achieve the Schatten threshold in the fragile settings, then this can be fooled by very few edges alterations. So they are very fragile. There are some recent results that are slightly more robust, so that these new results can afford polylogarithmically many changes in the edges. But this is a much smaller number than what we're looking for. We're looking for a constant fraction of edge alterations. It's also important to notice that there are some SDP algorithms that do not achieve the Schatten threshold, so they cannot perform weak recovery right above it. But on the other hand, they are immediately robust. So they get essentially the same performance with the fragile model and with this adversarial model. It's also interesting to notice that there are some adversaries that are known to change the threshold. So it's not clear a priori whether there is a price to pay for robustness here, whether this sharp phase transition is a fragile phenomenon. So we answer these questions in a positive way. We show that as soon as we are above the Schatten threshold, then efficient robust weak recovery is possible. So what does it mean? This means that this phase transition is a robust phenomenon, and indeed there is no price to pay for robustness. Okay, so in the rest of the talk, we're going to first see previous works, and now they fall short of proving this kind of result. What are the challenges that one need to face and to overcome in order to prove this result? What is the algorithm? And then the other contributions of the paper. Okay, so I want to phrase the problem as an optimization problem. So here I'm going to use capital X to denote the community matrix. And recall we're given a graph G prime, which is a perturbed version of a graph from the stochastic block model. In the optimization problem, we have some function, f of G prime or f of G, and we're trying to maximize it over a set of matrices S. And we should think of this as a set of matrices over which we can optimize efficiently. Now, there are two ingredients that we need here. The first one being correlation. So we want this f of G to be a proxy of the correlation of the matrix at hand Z with the community matrix X, so that the maximizer is close to the community matrix. The second ingredient we want is what we call low sensitivity. So the function f, of course, depends on the underlying graph, and should have low sensitivity in the sense that if the underlying graph is slightly changed, then the objective value of some z should also just slightly change. If we add these two ingredients, then we could perform robust weak recovery. So the idea is, the question now is, how should we choose this f of G? So it turns out that it's useful to look at the following matrix QS, which I'm also going to refer to as the self-avoiding work matrix. So entry ij of QS essentially is proportional to the number of paths between vertex I and vertex j of length S. And this number then being centered so that the conditional expectation of QS is X. This is an unbiased estimator of the community matrix. Now, previous works can be phrased in this way if we choose f of G as the product between Q of S and the matrix at hand. For example, if we choose S to be 1, then we are just working with the centered adjacency matrix. And this is what previously known semi-definite programs do. So an immediate consequence of this choice is that we have low sensitivity. So the objective value of some matrix does not change drastically if we only slightly perturb the graph. The problem with this is that even in the fragile settings, we cannot perform weak recovery at the Schatten threshold, but we can only get constantly close to that. A very different choice is to choose long paths, or say length that is logarithmic in the number of vertices. And algorithms that do that, they indeed achieve the Schatten threshold, so they can perform weak recovery at the threshold in the fragile settings, but they're not robust because they're highly sensitive. And to get an intuition of that, to just see that if we add or remove an edge from the graph, then there are many walks of logarithmic length that are affected by this. And so that's why these kind of algorithms are inherently fragile. So the idea is instead to choose something in between. So we want to look at paths that have constant but large length. So this idea has been used recently to design a robust distinguisher. So an algorithm that distinguishes between the stochastic block model and the Adversarial model. So now the question is, can this be used for weak recovery? So, okay, before trying to answer this question, it's useful to look at the robust distinguisher. So here, G0 is a graph sampled from the adversarial need distribution and G1 from the SPM. So the idea of the paper was to use the spectral norm as a distinguisher. But there is not really a gap in the spectral norm unless we truncate vertices of I degree. So vertices of a degree inflates the value of the spectral norms, but if we remove them, then we actually get some separation. And indeed, what they showed is that in the null case, the spectral norm of the truncated matrix is much smaller than the correlation between the matrix in the planted case and the community matrix. And this is clearly a lower bound of the spectral norm of QS in the planted case. And so we get, so it's clear that it's sufficient to look at this spectral norm to decide from which distribution the graph was sampled. Okay, so can we apply this for weak recovery? Well, it turns out there is a significant problem here, which is the following. The correlation between QoS bar and the community matrix is not a good proxy for the spectral norm of QS bar. So what I'm saying here is that the objective value of X is much smaller than the value of the maximizer. So the value of X is very far from being optimal. So this is the first problem. And the second problem is that there are many unrelated solutions that achieve the same objective value of X. And so a priori, it's not clear, given the maximizer of this function, how we could recover the communities. So this was not an issue for distinguishing because we only needed to show that the spectral norm was small for the Adversarial distribution. But it's a problem if we wish to do robust weak recovery. And so the question is whether can we use this matrix for this problem, or do we need something different? The key observation is that the community vector is correlated with the leading guided vector of QS. So this is sometimes called the push-out effect. If we have this correlation, then we can indeed, to some extent, recover the communities from the spectral norm of QS. Okay, so now we're going to see how to turn this into an algorithm. We're not able to show that there is this gap in spectral norm, but we're only able to show that there is this gap in for the T Schatten norm. And here T is some value that is smaller than log n. So the T Schatten norm is the 1/T root of the trace of the T power of a matrix. So notice that if T is larger than log n, then this is a very good proxy for the spectral norm. But if T is smaller than log n, then the gap between the T Schatten norm and the spectral norm is larger than the gap where we hope to show here. And so this is not a good proxy for spectral norm. There is also another caveat here, which is that there is no gap if we don't truncate the graph. And so we need to remove vertices of I degree. But removing vertices of a degree, then we lose the conditional independence between the edges. And this makes the distribution of the stochastic block model very complicated. And in particular, the problem for us was that this made the proof explode in size. So the paper went from 40 pages to more than 200 pages. Okay, but once we have this gap, we now have we can build our algorithm. So we're going to maximize the correlation between this QS bar and the matrix Z. And the constraints that you see on Z are just PSDness, so that we can efficiently search over the cone. And the bound on the trace of this power of Z is to ensure that the value of the maximum is the value of the T Schatten norm of QS bar. Now, this algorithm can be used to perform weak recovery at the Kessen signal threshold. And it can also be made easily robust. And it's sufficient to ensure that the matrix that we're looking for is approximately flat. So we add these additional constraints, and this will, the consequence of that is that we have low sensitivity, and so the algorithm is immediately robust. Okay, so let me spend the last few minutes outlining the other contributions of the paper that we haven't discussed. Of course, the main one is that we show that the phase transition at the Cassian threshold is a robust phenomenon. So we have an efficient and robust algorithm that performs weak recovery. To do that, we had to study the SBM distribution even after truncation, and so we needed to develop very sharp and strong tools to do that. So the hope is that they can be applied elsewhere. Another thing that we did not discuss is that our original algorithm succeeded with low probability. But it turns out that you can use robustness to boost the probability of the algorithm. And this technique appears to be very general. And so I encourage you to look into the paper to read about that. So, and also let me conclude by saying that it would be nice to have a simpler analysis of the algorithm. So this is all that I wanted to say. Thank you very much.